the Doppler effect. We've looked at two-point interference. We have looked at standing waves. Okay, this is the last little bit.
I want to talk to you about before we go to the park.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
And I have to, I can demonstrate.
Meow.
So what time does the costume parade start?
The parade?
Yeah, so the judges can give out prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. We look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, it's time Peter Pan.
I got a handful of pixie dust with your name on it.
No, you don't. I get what Sheldon's supposed to be.
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it. Now the Doppler effect. All right, I had a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Okay, so the key bit there was when he explained it very, very, very quickly to Penny. Okay? The apparent change in frequency. Okay, that is what we are going to have a look at. So, sometimes very difficult because we are also moving in relation to an ambulance or a police car, but as they go past you, if you are stationary, okay, it sounds different depending on where the source is compared to you. Okay, so if it is coming towards you, okay, we have this sort of chunk on the right hand side where we have a point source, but that point source is moving. And because it is moving, each of those wavefronts eventually get bunched up together. Okay, and so it appears to us, an observer, that the wavelength is quite short. Therefore, it has a high frequency and a higher pitch. Okay? As it moves past you and it is moving away from you, we now have this sort of section on the left, where because our source is moving away, our wavefronts appear to be more spread out. Okay, and if we have a longer wavelength, right, our wavefronts are more spread out, we have a lower frequency, and so we hear a relatively lower pitch. If we are perpendicular to our source, okay, so it was directly next to us, it is not coming towards, it is not away, it's kind of at that like equilibrium point, right, that is the actual frequency. Okay, and that is what any drivers of that vehicle would hear the whole time, because they are moving with the source. So this only occurs if there is a difference in movement or motion between the source and the observer. Okay, so you driving the ambulance, okay, is not going to hear this effect because you're moving with the source. Okay, it's only when it is coming towards or away from you that those wavelengths change, and so the pitch changes. Okay, we can get this with water and light as well. We particularly use it with light and talk about things like redshift and blue shift, and what we can do is we can work out whether something in space is moving towards us or away from us because of this effect.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency. And if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect. the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look at your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves mean a redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distance.
This is where our new formula comes in. So, if our observer, if our receiver is behind, or our thingy is moving away from us, our object, whatever it is, okay, we are needing to change the velocity that is happening. So in your formula, write down the bottom, okay, the black one is the one that you get given, okay, and the plus or minus in that, okay, you are either going to use plus or you are going to use minus depending on whether the object is coming towards you or moving away, okay. So even though it does say plus or minus there, you have to pick the right one depending on if it's moving towards or away from you, okay. So if it is moving away from you, okay, over this left-hand side, it has both versions, you need to add the actual velocity of the wave and the velocity of the source together, okay. So V with the subscript W is the velocity of the wave. How fast is the wave going, right? For sound, it's usually 340 meters per second. Okay, but that may change and they will give you that, usually give you that value, okay. The other bit, velocity of the source, so that is how fast is the ambulance going. So what we have, our F dash is our apparent frequency. Okay, what do we as the receiver hear as it is moving towards or away? Okay, our Fs, okay, on that very right hand side of the equation, is the actual frequency at the source. So what our ambulance drivers would be hearing. So if we are behind our source and it is moving away from us, we have a longer wavelength, so a lower frequency, so a lower pitch if we're looking at sound, or a bluer, more purpley light. So we are therefore adding the velocity of the wave to the velocity of the source in our equation. When we are looking at an oncoming or approaching source, okay, so it's coming towards us, we are in front of it now, okay, we have a shorter wavelength, those wavefronts are all bunched up together, okay, so a higher frequency, a higher pitch. We are then going to, in this case, minus our source velocity from our wave velocity. Okay, so they're both on this side over here. Okay, source receding as it is moving away from us. We are behind it. Source approaching, we are in front of it. It is coming towards us. Okay, so for this scenario, we are at this side. and we are minusing. In this scenario here, we are adding. Most commonly, we hear it with sound, right? We hear the ambulance go past, we do all of that kind of stuff. We also use it in some other ways. So a speed radar most commonly uses the Doppler effect to work out if you're going faster than you should be. Okay, here's an example of using the Doppler effect to work out, in terms of our redshift, whether things are moving towards or away from each other. Okay, so we can measure the color of the light, okay, and we can use it to compare to other bodies nearby and work out whether they should be the same color or not. Okay, so those observations in terms of noticing that we had this redshift, okay, is the start of the evidence for the Big Bang Theory. The other thing is a sonic boom. As you get faster, okay, your wavefronts will be closer and closer and closer together. So the faster the thing is going, okay, that front end, those waves will be closer and closer and closer together. Okay, a sonic boom occurs when you are going so fast that all of those wavefronts are jammed on top of one another right in front of you. Okay, so instead of having all of those lines separate, okay, all of your wavefronts right in front of you are all on top of one another. And that sonic boom is created when they happen all at once. Okay, and you basically break that sound barrier, right? It is essentially a physical barrier where you have created this kind of wall of particles that are happening in a certain way, okay, and then you are going through that wall.